You also need to have the picture in front of you and the PDF. Do you have the PDF opened up?
I will.
Oh, no. You need the actual PDF because of what I've written on here. Because I'm going to use that because I can't draw. I'll attempt to draw it up here, but you need to have the PDF in front of you. I'm going to draw a little bit of it, but not all of it. Let me know when you have that up. Anybody else that's following along, you got to have the PDF opened up because of the extra stuff that I put on the picture. I think it's on there. Like there's a 55 and a 90 and an A. Yep.
How's the music? I'm not paying attention.
If you're reading, yes. Yeah, you can plug it.
Okay.
Do you have it now? All right, so zoom in on that picture. You just really need that picture. Okay? So the idea that we have here is we've got a loop of wire. Oh, where did the loop go? Oh, there it is. We have a loop of wire, and we've got a magnetic field. And for part B, we will need to address what's going to happen, which way it's going to rotate, and there's a couple different ways to do that, but this is the general idea. Let me get this straight in my brain. Picture this is the desk, so yeah. So we've got like this kind of a thing here, and we've got a B field going like that. So we've got it at some angle, and the B field's going like that. Is that okay? All right. And as a result of that, we are going to either do that, or we're going to start to go the other way. Is it okay that we're going to have some rotation? Probably. Okay. Now, to get the amount of torque, if we have a loop of wire like this, okay, you can, I believe, on the AP test even, you can use this, okay, because this is based on the variables that do matter. Okay. Now, if you are confused on where this came from, there's a derivation in the text. If you don't understand the derivation, because as you're figuring this out, the individual parts could just themselves be problems. Does that make sense? But if you've got this rectangular loop, if you've got this loop of wire, okay, you can take n is the number of turns, the number of loops. That's like the multiply by thing.
I use this equation.
Oh, you use this equation, okay. I is the amount of current going through there, which that should make sense that that's going to have a direct impact on the amount of torque, because that's why we have a force to get a torque. Is that okay? Because torque is force times the lever arm. Yes? Okay. And then the area, this is the part where it comes from the derivation, okay? The area of the thing is going to be from the length times the width stuff, okay? And then B is the strength of the B field, which again, if you make the B field stronger, it would make sense that the torque would get bigger, because that's, you got the current, and the interaction between the current and the B field is why we have the force, that's why we have the torque. Is that all okay? So now it comes down to this part, okay? The angle, okay? And this angle phi, or theta, or whatever, okay, is the angle between the B field and the, what I will call the direction of the area. They will say normal to the surface, okay? But that's, if you shade this in, we're talking about like that. That's the direction of A, okay? So we need the angle between A and B. Are you okay that phi is the angle between A and B? Okay, because depending on how we're lined up, we might have zero torque, or we might have, I might be doing this the wrong way, but we might have zero torque or maximum torque, depending on what's going on. Is that all right?
Yeah.
Okay, so in terms of part A then, I think at this point, if we can figure out phi, I think it's just plug and chug. Okay, but let me check. But phi will be a little bit tricky. So they gave me B, I, yep, so we've got B, we've got I, and on the picture they gave us 0.7 meters and 0.5 meters. So we have this like rectangular loop, and it's 0.7 and 0.5. I might have those flipped around, okay? But can we get the area? Yeah. Okay, so we have the area slightly indirectly. So now it comes down to, can we get phi? Okay, can we get phi? All right, so this is where the picture in the book of the PDF comes into play, my PDF, for anybody that's watching in future years, okay? So in there, I have drawn on there, you'll see I've added an A to just represent area, and then I've got, let's see here, let me make this a little bit larger. And I put it on the picture because they have a nice picture, and obviously I can't draw real well, so. All right, so we're gonna have this, and then I got, do you see this part where I've got like an A above it in the picture? Okay? And this is supposed to be a perpendicular right here. So I wrote a little 90 degrees. They gave us this as 35 degrees. So that's the angle between like the base of the loop and the what they've called the y-axis. So it's like, if this is my y-axis, they've given me the angle in here. From like here to here. They've given me that angle. Is that okay?
Yeah.
But now that's not going to be the angle between the B field and my area, because that's like perpendicular to that. So I got to do a little bit of geometry to get to an angle that's useful. So if this is 90 and this is 35, all right, that means this right here will be 55. Is that okay?
Mhm.
Assuming Euclidean geometry. Do they do anything with non-Euclidean geometry? Has anybody done something where parallel lines can look like that?
I haven't.
But not in a class.
Not itself.
Not at South. Okay, all right. Just curious. I didn't think so, but you never know with an accelerated whatever class somewhere along the way. Okay, that was an aside. That's not important. Are you okay with the 55? So that means vertical angles are congruent. This is also 55. And that 55 is really important because visually that's going to help us a lot. Okay? So remember, this thing has turned out in 3 dimensions, right? So we've got like the coil of wire like right here. Can you picture like the coil of wire like right there?
Yeah.
Okay? And here's that direction of that area. The dotted line now is parallel to that direction of the area. Is that okay? And this was, I think, the positive y-axis. So that, and they said that was going to the right. That's parallel to the B field. So this line is parallel to the B field, and this line, this dotted line, is parallel to my direction in my area. So I want this angle right here. That's the angle between B and the direction of A. Are you okay that the phi is 55 degrees? All right, so now you can get your number. Oh, and the number of turns of coil, that should have been given as well. 75 turns, yeah. So we got our 75 turns times our current of, I don't know, I lost my place. Current of 4.4, so we got 4.4 amps. I think, was it 1.8 Tesla? 1.8 T?
Yeah.
And then we've got the cosine of 55 degrees. And getting that 55 degrees, you've got to be really, really careful, which is why I drew in the textbook one year, and then when I made the PDF, it was still there, so it turned into a hint for you guys. But I put it there because sometimes I would mess up the angle and I would get the wrong one. But you can't use the 35. It's definitely not the 35. What? Oh, I forgot about the area. Thank you. Let me just throw it out here. And the area will be the 0.5 times 0.7. And then whatever that equals. Is that okay? All right. So now for part B, we have to figure out which way it's going to rotate. Okay? So one way you could do it, and this is the way the key said it, was that you're going to tend to, where are you going to end up? Is it parallel? Oh, let me see. I always just refigure it out. This is number 40, what is this, 42?
41.
41. It says, as discussed in the text, when a current carrying loop is placed in a magnetic field, the loop tends to rotate such that its normal becomes aligned with the magnetic field. Okay? So they're saying that, we look at it from like here's that loop here, what's going to happen at 35? Is the 35 going to get bigger or is it going to get smaller? Well, it's going to tend to line up. Wait, what did they say? Line up. I lost it again. The normal of the loop. The loop tends to rotate so its normal becomes aligned with the magnetic field, which means that if we've got the area going this way, right? Okay, we're going to make it so that it's going to end up down here so that it lines up. Now, you could remember that, so that would mean that it would increase, right? Yeah, increase, or, okay, because I don't remember that off the top of my head, or you can just apply your right-hand rules and figure out which way is this thing going to rotate. So when I say the right-hand rules, which way is this going to rotate? So we have a B field going to the right, okay, or just look at the extremes. Look at here and look at here type of deal, okay? So if I'm here and I've got my B field going to the right, okay, I'm not going to have... let's see, we are going to have a torque. So we will have, wait, hold on a second. I feel like I'm missing something. Loops are determined magnitude of the net torque in the loop and state whether they're going to increase or decrease. Oh yeah, it had a current in it. Okay. So I got to pick some direction for the current. Oh, I might end up going the other way. All right, so let's say current that way, B field to the right, okay? So I'm going to get a force, current that way. I'm going to put the prop down, okay? All right, let me just look at the picture in the book. So if we've got for that, let's do for that bottom segment of wire. So the 0.5 meters right here. Yes, that? Okay. So let's say that we have, they gave us a direction of current. Okay, good. That's what I need. So on the picture, the current is going this way through that segment. Is that all right? So now we can apply our right-hand rule. And the part that's perpendicular is the current that is going up. Okay, the current's going up. And the B field is going to the right. Are you okay with current up, B component of the current up, B field to the right? So we're going to get a force that will go into the board. So into the board. Wait, didn't they say it increased? Uh-oh.
Well, it says statement of the 35 will increase returns.
And we were supposed to get increase, weren't we? Did I just get it the wrong way?
You said increase a second.
I said increase. Wait a minute. What direction is the current? Current down there is going to the left. Oh, that's at the bottom. That's not going to have B field to the right. Where's the pivot point? The hinge is over here. That's what I lost. The hinge is over here type of deal. So that doesn't matter. We're going to look at the other sides. So look at, here, I'm going to point so you can see what I'm talking about. I'm looking at that segment right there.
Oh.
We'll look at that segment. Is that okay? All right. So I'm going to attempt to draw that up here. So we got this. I'll make this slanted a little bit, and then like this down to here, and then all right. So I'm looking at in the book. I'm looking at this segment. Okay. And for that segment, the current is going down, and we've got a B field that is directed to the right. So we've got. There we go. How do I do that? We got current down, B field to the right, so we're going to get a force out this way. And here's your pivot point over here, right? So this door is going to open towards you. Is that okay?
Yeah.
Yep, I just picked the wrong segment because there is no torque there because of where the hinge is at, or where the pivot point's at. So the door is going to open this way, which means if this thing is swinging out towards you, this 35 degrees is going to get bigger. Is that okay?
Yes.
Yeah, sorry. This is the problem with going from an XY plane like this to an XY plane like this and then trying to use a three-dimensional aid. It took me a minute to get my head wrapped around. Just make the picture on the board really easy. Are you okay with that approach?
Yeah.
Okay. And you could have, it was pivoting about this point, so you wouldn't want to pick there. So yeah, it's pretty much this one. That's what's going to make it turn one way or the other. Either going this way or was the door closing the other way? Is that all right? Okay. Questions from anybody else? So increase based on the force outward on that far right segment. Okay, go ahead and stop that.